Continuing the discussion of molecular vibrations, I want to discuss a particular model that is very commonly used to describe these molecular vibrations, and that is the model of the harmonic oscillator. So this shows the HCl potential energy curve, like I showed you before, and then superimposed on that in the red curve is a parabola that is often used as a model. That parabola represents a so-called harmonic potential. And you'll notice that it is not a very good fit unless you are very close to the bottom of the potential energy curve, say down in this region. And very often vibrations about the equilibrium distance are small enough so that we are in that region, the region I circled, and the harmonic oscillator can be a reasonable approximation to describing the actual vibrations. So the harmonic approximation in general, we write the potential as 1/2 K times R minus RE quantity squared. So it's a parabola whose minimum is at RE. And for the sake of the HCl, I have given you specific values for these parameters. K, right here, K is 512.5 joule per meter squared, and RE is 1.275 times 10 to the minus 10 meters. In one of the problems that I ask you to do, which is essentially a problem in unit conversions, I want you to go into Excel and put in values right around this region from 0.1. So maybe put in values from around here, 0.1 to up here. Where's that? That's maybe 0.17 or so. Anyways, just roughly in that region, put in a bunch of values into an Excel spreadsheet and do the appropriate, and put in these values for K and R. Do the appropriate unit conversions to put the x-axis in nanometers, the y-axis in electron volts, and so put values into the spreadsheet and make an XY plot of this particular parabola. And you should kind of confirm what I've shown here if you've done your unit conversions right. In other words, say the potential energy at say about 0.11 nanometers should be right around 1 electron volt. So again, that's an exercise in unit conversions and doing graphs on Excel. Okay. So now I'm going to continue with looking at the particular solutions to the equations of classical mechanics for this problem. And I have reproduced some of the equations from my handout, and I'll switch to those at this point. So first of all, we make a change of variable to make things a little less messy, and we just say x equals R minus RE. So then the potential energy curve is centered on x equals 0. And so we can consider x to be equal to the displacement from equilibrium. Now, the harmonic oscillator is something you've probably discussed in physics before, and it was probably introduced in terms of force rather than potential energy. And this should be a lot, if remember force is dV dx minus dV dx, and that leads immediately to this equation, force equals minus kx, and that should be pretty familiar to you. So that k that appears in the potential energy expression, you've probably learned it as the force constant. Okay, and it's with a minus sign because it's a restoring force. The equations of motion, as usual, are given by this. And remember that P, which is the momentum, which is ordinarily mass times velocity. In this case, we use reduced mass, and and P is equal to mu, the reduced mass, times dx dt. And then, so this leads immediately to this equation, this differential equation for x. And the thing to remember, x is not our independent variable. X is our function of time that we are trying to solve for. I will assert without proving it, but it should be pretty obvious, that x is the solutions to x are going to be sine and cosine functions. Why is that? Well, notice that if I take the first derivative of a sine function, for example, I get a cosine function, and then if I take the derivative again, I get a minus sine function. I get the sine function back with a minus sign, and that's exactly what this equation shows with some constants involved, that the second derivative of x gives me x times the same function times a negative constant. So we can show that solutions of the form x of t equals x naught times sine omega t, or x naught times cosine omega t, that these will solve it, provided we have the right value of omega. And just to remind you of some things, omega is sometimes called the angular frequency. So angular frequency, and the ordinary frequency, the angular frequency is related to the ordinary frequency nu by 2 pi nu equals omega. And nu represents a number of oscillations per unit time. So now let's demonstrate that these things are solutions. We'll let x of t be equal to our presumed cosine function, x0 cosine omega t. We take the first derivative of that, dx dt, and remember the derivative of cosine is minus sine. We bring the constant omega out front, and we have minus x0 omega sine omega t. And then we take the derivative of that, so that's the second derivative of x with respect to time. And remember, the derivative of sine is cosine, and so d squared x dt squared is equal to minus x0. We bring another omega out front, omega squared cosine omega t. So now the question is, does this satisfy the equation minus kx equals mu d squared dx dt squared? Is that true? Well, it depends on what the value of omega is. So we can put our second derivative in for this, and we have minus kx equals minus x naught mu omega squared cosine omega t. And so then at this point we can see that cosine omega t times x naught, this is just our original function, x of t. So that gives simply that minus k times x of t equals minus mu omega squared x of t. And we can see that this will, so now at this point we can take xt out of here, and we can see that this solves it only in the case where omega is the square root of k over mu. So I can see that the frequency of the oscillator, given by this angular frequency here, the frequency of the oscillator depends on the force constant and on the reduced mass. And this is something that should be familiar to you when you cover this in your physics course. A couple of things to note here. First of all, the solution, either the sine or the cosine function or any combination of the two will satisfy the equation of motion. Also, the other thing is that the solution, the frequency that you get does not depend on x0. So for example, if I'm making a graph of one of these, say this is x as a function of time, and I'm doing the cosine function, and I have something like this. This quantity right here, this is x0, the maximum displacement. Well, if this solves the equation, then this function, same frequency, but different x0 also satisfies this. So an oscillator, harmonic oscillator, has the same frequency regardless of the maximum displacement. And again, this is something that you should be familiar with from your physics course. So another problem that I want you to do is to looking at solutions of this from the definition of momentum P and potential energy. So we would have from P equals mu dx dt. Take either solution for x as a function of time, and then use this expression to come up with an expression for p as a function of time. Then in turn use this to find kinetic energy as a function of time from the expression kinetic energy is p squared over 2 mu. And then do the same thing. Now potential energy, again treating x as a function of time, find potential energy as a function of time from the expression for potential energy 1/2 k x squared. Substitute in our sine or cosine function for x. And then we will then write total energy as a function of time. Add these two together. E equals T plus V. And you should find that this is a constant. And to do that, you might have to use a very commonly known trigonometric identity. And the final problem that I want you to do is to find a value for the frequency of the model HCl harmonic oscillator, using omega is the square root of k over mu, from before, you should have a value of mu in SI units, and then find the frequency is equal to omega over 2 pi. And that would be it for the assignment for the harmonic oscillator potential as a model for a vibrating diatomic molecule.